Hello and welcome back. This is going to be our first of 4 optimization problems, and the goal of this problem is to find the dimensions that will minimize the cost of building a rectangular area, and they give us information about the material used for the length and the width for our rectangle. So the first thing you want to do is take a look at what you have for constraints, and you want to look at what you have for optimization. And they tell us in this problem here that we're going to have the area always locked in, which is length times width, as 240 square feet. So that right there is our constraint, because no matter what solution we find for our problem, it must have this fixed area. The next thing we want to do is we want to look at our cost. And our cost is going to come from building this box. And if we think about our rectangular area, we're going to have the length twice and the width twice. And normally the perimeter is the sum of those 4 dimensions. But in this case here, we're going to be looking at the cost coming from building out those dimensions. So for the width, it's going to be $6 per foot. And we have 2 of them. So it's going to be 2 times 6 times W. Again, 2 sides, $6 per foot, W, number of feet. And then for the length, we have 2 sides we're building. That costs $10 per linear foot, and we're going to have L, number of feet, for our lengths. So our cost function actually has 2 variables. It's 12 times W plus 20 times L. And in Calc 1, we have to make sure we get this down to a single variable. So the idea is to use our constraint above, which was L times W equals 240, and use that information to isolate one of the variables. So in this case, let's go through and eliminate the L by dividing both sides by W. So L is 240 divided by W. We're now going to take that value of L and substitute it into our cost function. And so our cost function will now have just one single variable, and it's 12 times W plus 20 times the L we just found, which is 240, divided by W. Not L, but W. All right, next up, simplify this down a little bit. So we're going to have our cost function, C of W, is 12 times W plus 4800 over W. All right, so now we want to minimize this cost. And this is where we're going to apply our calculus. We are going to go through and find the minimum by finding our derivative and looking at critical numbers, and then investigating the behavior of the function around those critical numbers. So the idea is to take the derivative, which is just 12 minus 4800 times W to the negative 2, which is just 12 minus 4800 over W squared. And again, remember our critical numbers come from either a place where the derivative is equal to 0, but in the domain, or where the derivative is undefined. And again, you'll notice that it could be undefined when W is equal to 0. But this whole problem more or less implodes if W is equal to 0, because if that happens, there's no way you can have an area of 240 square feet. So we know that W is not equal to 0. But this derivative can be equal to 0. And when you set it equal to 0, you're going to have 12 minus 4800 over W squared equals 0. If we multiply through by the W squared, which we know is non-zero, we end up with the algebraic equation 12W squared minus 4800 is equal to 0. So 12W squared is equal to 4800. Divide both sides by 12. And W squared is equal to 400. So W is going to be plus or minus the square root of 400, or plus or minus 20. And again, these are feet. So you notice right away that you cannot have negative 20 as a dimension for this rectangle. So we're going to look at just having a positive option for the width, So when we draw our number line, it's going to start at 0. And again, we have a critical number at 20. So we're going to put a 0 above it. And now we need to test out what's happening on both sides of our derivative, or both sides of our critical number in our derivative. So if we substitute a 1 into c prime, you'll notice quickly that it is negative. So at 1 and on this entire interval, we have a negative derivative. And over here on this side, if you take something such as 21 or 100 or 1,000, you notice that c prime is going to be a positive number because that second term just basically goes to 0. So we know that our cost is decreasing for values of w less than 20 and increasing for values greater than 20. So we do have ourselves a minimum at 20. So we have the minimum cost when w is 20 feet. And we can now backtrack to get the other dimensions. We know that L is 240 square feet divided by W, which is 20 feet. That ends up being 12 feet. And then our cost is going to be C of 20. And we saw earlier that was equal to 12 times W. So 12 times 20. And then it's going to be plus 20 times 12. So that's 240 plus 240, which is going to be $480 for our cost. All right, so that right there is the solution for this optimization problem. And again, if we look back at the beginning, the idea was to minimize the cost given a fixed area. We model the cost. We use the area as a constraint to reduce our function down to one variable. Apply what we've learned in the chapter about optimization, finding the derivative, critical numbers, studying the derivative, and then answering the rest of the question.